Okay, this is going to be uh, a review for the last test. I'm just going to go over it and go through my thought process. The scores weren't the best on it, so let's learn from your mistakes. I would suggest before starting a problem, maybe do the problem again and see if you get the same thing I get, and then just move on with the video. Okay, so go ahead and pause it and then unpause it and we'll come back. Okay, so when I'm reading through this question, I read through it and I say, okay, well, they want an interval. So my thought process is there's either mean intervals or proportion intervals. That's it. Okay, so that's what I'm trying to figure out. Is this a proportion or is this a mean? And generally, it's in the data that they collected. If the data is quantitative, then it's going to be some sort of a mean. If the data is categorical, it's going to be a proportion, or it might even be a chi-squared, but there's no intervals for chi-squared, so it can't be that. Okay, so let's see what they measured. The amount of vegetation, so that's going to be quantitative. And another thing is the question's talking about mean right here. It says mean, so we know it's a mean. And all these are set up as a one sample, because after I do that, I do either it's a one or a two sample, or it might even be a paired. But in this case, it's just a one sample because they took 9 plots. Okay, so from there, I'll go to my formula sheet, and I'll go to where it says confidence interval, and it says statistic plus or minus critical value times the standard error. So we got statistic plus or minus critical value times the standard error. So all these things are the same. And if you're not sure what the statistic is, if you just go to your formula sheet, these are your statistics. So these are for proportions. The second thing is for means. It means. So x bar is your statistic. And the x bar here is the average of the 9 plots, which was 4.3. Now most of the people that missed it was because of the critical value. Okay? Critical values for means, if S is being used. So the question is, where did this standard deviation come from? That standard deviation came from the 9 plots. So in that case, it's S. It's not sigma. Okay, in that case, it's going to be a T. It's not going to be a Z. That's where most people messed up on this question. They use Z. They put in 1.96. They picked this. They picked this one. That's not right. None of these are right. These two are wrong. It's not that. It's not this, because it's not a Z. It's a T. It's pretty much always going to be that way. It's always going to be a T for means. Okay, so there was 9 plots, so I'm going to go to 8, and I believe they said 95%. Let me just double check. 95%. So I'm going over to 8 for the DF. 95, 2.306. Okay, so now, I guess we know it's not that, so it has to be either that, or that. Okay, so this is going to be 2.306. Now, to get your standard errors, you go to your formula sheet, and all the standard errors are on the back of the formula sheet. Since this is a mean, and we got one population, it's going to be S over the square root of n. So S in this case was the 1.5. That's the standard deviation from the sample. And then n is 9, so it's the square root of 9. So the square root of 9 is 3. So the answer is E. Okay, go ahead and take a pause the video and then come back. Okay, so they're asking for a confidence interval, so it's the same idea. It's statistic plus or minus critical value times the standard error. Okay, now the statistic here, since we're estimating the slope, we're trying to estimate the true slope, so the statistic is going to be the sample slope. Now, if you didn't know that and you went to your formula sheet, I'm on the back side of my formula sheet. That's the front side. Here it is right here. These are for proportions. These are for means. These are for slope. So what's my statistic? Little b. So little b is right here. This is little b. Everything on this second row here, it has to do with slopes. So my statistic is going to be 0.161, so I could get rid of A and I could get rid of B. Now plus or minus. This is where all the problems came. This is a T star. This is where the problems came. We have to know our DFs. The DF in this case is however many people we sampled minus 2, not minus 1. So the DF here should be 20. Okay, so let's go ahead and go to our chart. Here's my T. Okay, so we got 20, which is the last shade, and I forget what confidence it was again. 98. 98 and 20, 2.528. 2.528. It's going to be this one right here, another C. And this is the standard error right here. They give you the standard error. So 2.528, and the standard error is 0.073. You don't have to do any formula. They've already done the formula. The standard error formula is very complicated for slopes. It's this formula right here. See, this is slopes. It's for slope. Standard deviation for simple linear. It's this standard error. It's this formula down here. Or this one right here. It's tricky. Or S of X. No, it's this one right here. S of B. Okay, and they give you S and they give you S of X. S is the standard deviation of the residuals, and S of X is the standard deviation of X's. But you're not going to have to do that, okay? Maybe on a question 6, but not on a multiple choice. They're just going to give it to you. Okay. Go ahead and pause the video and come back. Okay, is there convincing statistical evidence? So this is either going to be a mean problem, it's either going to be a proportion problem, or it's going to be some sort of chi-square problem, or maybe even a slope problem. Okay, so there's this large city, blah, 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 a random sample. Okay, so they asked them a question. This is categorical data. Categorical data. They're saying, like, out of 341, 94 opposed. I have to make sure. School age. There's the school age. So out of 230, 994 opposed. So that means that's a count. This is a count. So it can't be a mean, and it can't be, and it says proportion right here too. So without even doing data, I mean, it says proportion. So it's not going to be that. Okay, it's not going to be a slope. It's going to be a proportion. And then it says 2 population proportions. 2 population proportions. So this is a 2-prop. It is a 2-prop z-test. 2-prop z-test. Okay, there's 2 proportions. It's a 2-prop z-test. So go to your calculator. I know it's 2 proportions because they took a sample from city residents with children and a sample in the city without children. That's the difference between them. So to do this, you do stat, go over to test. It's a 2-prop z-test. It didn't say interval, it says evidence. Click that. Okay. Now, X's are counts, N is a sample size. So out of 230, 94 opposed. So there's 94. There's the 230. Boom. Okay. Out of the other group, it was 341, 147. So that's 147. And if you're doing this the long way, that's not a good idea. You have to do these things by a calculator. Because once you do this, it goes so fast. Now, they're asking for a difference. They didn't say one was bigger than the other one. So if they're asking for a difference, it's a not equal to. Okay, 94, 147, just double checking my numbers. I get a p-value of 0.59. This is my p-value right here, 0.59. So I don't want to go into too much detail, but your null here, if you set up a null, will be p. What is the difference? With children equals the p without children, and your HA is going to be p with children is not equal to p without children. This is 0 in the middle. If the p-value is 59%, then that means that whatever difference you got in your sample, whatever difference you got, with these two p-hats from both samples was not significant. It wasn't that far away from zero enough to believe that there's a real difference. Okay, they're just giving you the p-value definition. So really, you're looking at B and you're looking at D. Okay, yes, because the sample proportions are different. That's not enough. I mean, two proportions could be different. That doesn't mean that something's significantly different. Okay, they're asking further if there's a difference. Okay, we got a p-value greater than alpha, not less than alpha, so it can't be that. Okay, so it's either B or D. Okay, because probably observing a difference is at least as large as the sample difference. We don't have a sample difference. Or I guess we do have a sample. It's greater than. Okay, it's this one because this last sentence they put in here is very important. If the two population proportions were the same. Okay, this is the definition of the p-value. Okay, it's this one right here. If the two population proportions were the same, then we expect this difference to be 0. Well, it wasn't 0. It was a little off from 0. You shade here, you shade there. This is the p-value. Both sides is the p-value. So this p-value is so big, the observed difference is not that unlikely if the two p's were the same to begin with. So hopefully that makes sense if you missed that one. Okay, which of the following test statistic? Okay, this is very important right here. Make sure you pause it and read the question and come back. That's very important. Mean difference. A mean difference is a paired. I didn't even read the question. I mean, I did, but I'm just saying, like, as soon as you see mean difference, you know it's a paired test. Okay, that's the mean difference. What's a two-sample t? A two-sample t is the difference in means. It's very helpful if you're good at this, to be able to tell the difference. They're baiting you into picking a two-sample t test, but you should be doing a paired test because it says mean difference. Okay, so a test statistic is the statistic minus the parameter over the SE. And this is in the do section of any test. Of any single test, it's the test statistic. Okay, and you can see this formula on your formula sheet on the front page. Test statistics. So the test statistic is the do sections for your hypothesis test and confidence intervals for a confidence interval. So you just have to know what the statistic is. Okay, so there's 50 candidates. And there's two sections. So assume this is the first candidate. Each candidate's taking both sections. So they get the first section, and they get the second section, and they measure the difference. And then the second candidate, they get the first, and they get the second, and they get the difference. And there's 50 candidates here. So the data is the average of all the differences, and that's called X bar diff. Okay? And what's X bar diff? What was the average of the difference? I'm not sure if they did second minus first or what. It probably says it, but it's probably second minus first because they're getting a positive difference. So the statistic here is the X bar difference. The parameter is that, first minus second. Sorry, first minus second. So they did first minus second. The parameter is your null. And if you were doing a test on here, you would say mu diff is equal to 0 because it's always equal to 0 for these. And then this is going to be over the standard error. So what's the X bar difference? 10. What's the standard error? If you look on, it's considered one sample. It's not considered two samples. This is right here. Sampling just one sample for one population. It's S over the square root of n. S over the square root of n. So it's 8 over the square root of 50, which is right here. Now 4 was a missed one. 1, 2, and 3 aren't that horrible. This question is tricky. 4 is tricky because it's very easy to bait somebody into doing a two-sample t because two-sample t's are more popular. A two-sample t would have said significance and the difference of means. What a two-sample t would have been if they took the 50 people and made 25 do the first and do 25 do the second, and they got an X bar here and an X bar here and compared them. That's a two-sample t. If you do 50 people and both people take the same test and you compare how that person did against themselves, that's a paired test. And this is the test statistic. You might even have known it was a paired. You need to find the link to the test statistic. The test statistic is the do section of any hypothesis test. Okay? And just to let you know, it would have been very difficult to figure this out, but you could run a test. It's just called a t-test. You could have ran a t-test on there if you wanted to, but it's really not going to help you because you need to know the formula. Okay, it looks like they have some intervals here, so we're looking for an interval. Here we go, 90% confidence interval. For what? For the mean. Okay, did they say for the... See, this is the thing. I know it's a mean problem. So it's a mean problem. It's either going to be a t-int, a two-sample t-int, or a paired t-int. And a paired t-int is done the same way as a t-int on your calculator, okay? But these would be different. Okay, so I'm looking. Do we have one sample or do we have two samples? I already know it's probably going to be one sample because it didn't say for the difference in means. Or it didn't say the mean difference. If it was a two sample, it would have said the difference in means. If it was a paired, it would have said, hey, let's estimate the mean difference. We're just doing the mean. We're just doing the mean. So this is just going to be a t-int. Okay, 16 people who had heart attacks. Of the people in the sample, the mean was 264. So since that's the sample, that's 264.70. And the standard deviation was 42.12. Okay, all these little things are very important. Okay, so now this is going to be a t-int. Don't do it the long way. I mean, I guess it's not horrible to do it the wrong way, but it just takes too much time because you're going to be doing this, 264.70, plus or minus. Now you have to go find a t-star. Okay, now this part wouldn't have been bad because this would be 42.12 over the square root of how many people they picked, the square root of 16. But then once you find all this stuff, you actually have to go to your calculator and put it all in. And a lot of mistakes are made putting this stuff in. So your best bet is just to be ready to use your calculator. Okay, be ready to use your calculator. Boom. Okay, over here to test t-int, t-interval, number 8. Okay, now we need to know the average. They didn't give me the data. So it'll be 264.70 and 42.12. That's the standard deviation. They picked 16 people. Let me just double check my confidence level. I think it was 90, so 0.9. Let the calculator do the work. Everybody's running out of time, and partly because they're trying to do it a way that takes too long, because this doesn't take long. Okay, 2428316. The answer is C. Just let the calculator do the work. If it's a formula, you're going to have to get to work a little bit at it. But if it's a p-value, then you just or an interval, do it on the test. Okay, go ahead and pause it and come back. Okay, so this company produces produces millions of 1 pound packages of beef every day. Okay, good. They're going to take 1,000. So they took a random sample of 1,000 and found 40 packages to be underweight. Now 40 is a count. Okay, the percent is p hat. So if you take the count and divide it by how many you check, that's p hat. That's p hat. P hat's sort of like an X bar of the proportion world. X bar is like the average for the mean worlds. They're both statistics. Okay, convincing evidence. So it's going to be some sort of a test that more than 3%. So your null, your alternative. So here, this would be point equals 0.03 because it says, is there evidence that's more than 3%? Well, what was our p hat? 4%. Okay, so either this 4% is due to chance or this 4% is unlikely to happen. Okay, it's either due to chance or this 4%'s out of the ordinary if it's really 3%. Because it's really 3%, this p hat should have been 3%. Okay, so When you start seeing a difference between a p hat and a p, it's either by chance or it's so different that you don't believe the 3%. Okay, so we have to go run this test. So it's a proportion. It's categorical data. That first meat that went in there, it's either underweight or it's okay. The second one, it's either underweight or it's okay. And you count up the number that were underweight and it came out to be 40, which is a count. This is not a mean problem. It's a proportion problem. Okay, now we know it's a proportion problem. Let's go run the test. Okay, stat over to, this is a 1 prop z test. 1 prop z test. We have one sample and it's a proportion. Okay, 0.03. We're testing to see if it's bigger than 3, so we're going to assume that it is equal to 3%. 40. We're underweight out of 1,000. That's how you get your 4%. And we're testing to see if it's greater than. That's it. This is going to give me the p-value. Once I have the p-value, we'll be able to make the decision. 0.032. 0.032 is the p-value. So the p-value equals 0.032. Okay, now they have an alpha of 5%. So here's the p-value. Here's alpha. The p-value is less than it. So if the p-value is low, the null must go. So we're going to reject HO. Well, if I reject HO, then who do I believe? I believe HA, which means we have evidence for HA. Okay, because the p-value is less. Okay, is there evidence of a difference? Here's the evidence. Does the data provide convincing evidence that's more than 3%? Well, I believe this. That should be a more than, not an equal. Do I believe this? Yes, I believe that. Okay, well, why do I believe that? Because the p-value was less than 5%. Okay? Yes, because the p-value is less than 5%. Is there evidence of a difference? Yes, there's evidence of a difference because I believe this. Or do we have evidence that's more than? Yes, because it's more than. You have to have this concept down. A lot of people are missing 6. You can't miss 6, okay, and expect to get a 3. If you don't have this concept down, it's going to hurt you when it comes to, getting a 3 or higher. Okay, this is a great question because it kind of tests you like it's a question about hypothesis testing, and it's also a question about what can you do if you get results that are significant. Okay, so they took 80 volunteers and they put 40 and 40 and randomly assigned. These people all drank soda. These people drank water. Okay, and then at the end of the study, they found evidence that people who drink soda on average had a higher percentage of fat than people who did water. So these were the water, those were the soda. Okay, now the question is this an experiment? And the answer to that, or an observational study? Because the scope of the study is different depending on which one it is. Okay, since you randomly assign these people, okay, and I think they even controlled their diets or something like that, just in case. Okay, so, and if this is an experiment, you can say cause and effect. If you see a difference, you can say, oh, it must have been the soda that caused the change. If it was an experiment. If it's an observational, then this is no cause and effect. Okay, so this question's basically saying, okay, well, they found evidence that it was the soda. Can we say it was the soda? Okay. Causes. It could be that one. Drink causes. Causes. Cause and effect can be established. There's an association. These would be for observational studies. This would be the answer if they just went and got 80 people. They could have taken 80 people randomly and just said, hey, do you drink a lot of soda? Yeah. Oh, this is you. I drink a lot of water? Yeah, this is you. Okay, if you don't make them do it and control other things, then if you don't do that, then you can't say cause and effect because it could be other variables. But if you randomly assign them, then you're allowed to do that. Okay? Now, when it comes to who can we generalize this about? Can we generalize this to all adults? Can we generalize it to people who drink soft drinks? Or can we generalize it to adults similar? Now, the question of that is, how do we get these people? They are all volunteers. And whenever they're volunteers, we're only allowed to generalize to people that are similar to the ones in the study. Okay? You can't generate this about all adults unless you randomly selected from all adults. Okay, so that's that one. This is the trickiest one on the test, to be honest. Okay? This one and the other one I was talking about was sort of tricky too. Okay, so they had this study. Okay, so this is the body fat before and after for 10. So most people are already thinking matched pairs. I mean, that's the go-to wrong answer. Most people are thinking, oh, this is a matched pair. And this is the best wrong answer. Okay? And the reason why you're thinking matched pairs is because you got a before and after. You got 2 results on that person, 2 results on this one, 2 results on this one. But what are we trying to achieve here? Are we trying to do something for the mean difference? We're trying to test a mean difference to say something like, oh, the after, after is going to like decrease your body fat. Okay, is that what we're doing? Or are they trying to predict? Here you go. Knowing the body fat before helps what? Helps predict. So in this case, this is the before and this is the after. And these are all dots on a scatter plot. So if you know this before, does it help us predict after? Okay, so this is and you only could do that if there's an association. Well, how do you test for an association? You do a linear t-test, linear regression t-test. Okay, so if you're trying to predict a y based off knowing an x, then you'd have to have an association, right? Because if it was like shoe size and IQ, I'm trying to predict IQ off shoe size. If you run a t-test, there would be no association, and you can't do it. But these body fats, they look like they're all sort of matching up. So if I know this is a 20, do I expect it to be like 10? Do I expect it to be like 15? Or do I expect it to be around 20? Well, I expect it to be around 20 because I know there's an association because I ran a linear regression t-test. So that question, I mean, I don't know if it's tricky, but I just noticed when I ran the Scantrons, a lot of people missed it. Okay, here's the test. I'm just attacking things like mean. Okay, 1,500 a year. So there's some report. It should be 1,500. Now we test if it's greater than 1,500. They took a sample of 120 people. They got a p-value of 0.25. So here's your null. Pause it and go back. Pause it. See if you can get the null before you come back to the video. Okay, so some report says it's 1,500. So okay, let's say it's 1,500. Now we're going to test to see if it's greater than 1,500 based off the sample average. They took 120. They ran the test back for you, and they got a p-value of 0.05. Sorry, not 0.0, 0.25. Okay, if the p is low, the null must go. If the p is high, the null will fly. Okay, this is that's a bigger p-value than any reasonable alpha. So this is bigger than alpha now. Now what are we going to do? We're going to fail to reject H0. So we're not going to reject that. So you can't say it in words, but this is what you should be thinking about. We believe this. That doesn't mean we have evidence for it. We don't have evidence for this. You have to be really fast at this concept. This is all the due to the conclude. This is due to conclude. You can see I'm pulling these questions off 1 or 2 tests. There's a lot of this stuff. Okay, so it's going to be something with not convincing evidence. Can't be there's convincing evidence. So it's either one of these two. Okay, that looks good. By any sample of 120. No. This decision is always about the population, not about what happened in the sample. So your answer here is number 9. This is a question, if you want to get a 3 or higher, you really want to make sure you don't miss it. Okay, 10 is turning out to be hard, and I gave this. This is the third time I'm giving these type of things, and it might be a little bit more tricky, but overall it's not too bad. They want to investigate the relationship. Okay, whenever they say relationship, it's either going to be a chi-square test or it's going to be a linear regression. Because like a relationship, that's a relationship. Okay, it could be like a segmented bar graph. That's a relationship. Okay, so it's either a chi-square or a lin reg. This is for quantitative data. That's for categorical data. Okay, and if it's chi-squared, so you have to know your DFs. Okay, so the residents were candidate per word, and each resident was classified into 3 age groups. So age group 1, age group 2, age group 3. And they were looking for the relationship between age, which I have here, and the preference of 2 candidates. So that's candidate A, candidate B. So this is your table for your chi-square. Okay, the test statistic. Okay, let me go to my formula sheet. Test statistic. Here's your test statistic. Chi-square statistic is a test statistic. Okay, so this is it. Okay, they ran it for you. We already know that the chi-squared equals 3.7408. Okay, approximately what is the probability that the observed responses would be as far or farther from the expected if there is no association? So if there's no association, if you do a bar graph, then these things all match up. These things match up. In that case, if there was no association and they all match up, your p-value would be, if the observed were all the same as expected, your chi-square would be 0, and your p-value would be 100%. Okay, so if you look at this formula, if the observed was the same as the expected and you subtracted that, you'd get 0. If the observed were the same as expected on the next category, that would be 0, and chi-square would be 0. But in this case, they weren't, because the chi-square was 3.7408. If you draw a line to the top, this is the p-value right here. That's what they're looking for. They're looking for this p-value. Okay? Okay, so it's like, how do you find this? Chi-squared. Let me get rid of some of this stuff. You're going to do chi-squared CDF. There's 2 calculators. You have the nicer calculators, which have a lower, have an upper, have a DF. If you don't have this calculator, this is the order that you have to put it in. Because some of them just have a parentheses right there. This is the order. So what's the lower? The lower is 3.7408. I want that chi-squared. Draw a line to the top, shade to the right. Upper, put in a big old number. This is where people are struggling. Know your DF. Know your DF. There's 2 candidates and there's 3 age groups. So you take 3 minus 1 times 2 minus 1. So it's 2 times 1. So your DF is 2. Okay, to get the chi-square CDF, it's second vars. It's like we're normal CDF and we're T-CDF, chi-square CDF. Okay, now I'm going to do, just check to see what this is, 3 point. Okay, pick a big number, and the DF was 2. Everything's about concept, guys. If you know the concepts, you can go. Like to me, we just did this. This is chapter 12. Shouldn't be too hard, okay? But when you look at the scantrons, most people miss this problem. Okay, let's look at this one. Pause it and come back. I mean, you did do it on Friday, but okay. So, is there significant? They give us provide convincing statistical evidence that 5% that died. So this is a hypothesis test. So now, if it's a hypothesis test, it's either going to be a mean, it could be a proportion, it could be a chi-square, it could be a linear regression, but probably it's not going to be. It's a mean. Okay, now you have to be a little bit careful here, because once you have 2 groups of data, either it could be a paired, or it could be a 2-sample T. 32 dogs were randomly assigned. So they took 32 dogs and they put 16 here and 16 here. And these got the J and these got the W. They got an average here, they got an average here, and then they compare. This is the difference in two means. This is a two-sample t-test. Two-sample t-test. Okay, what's my null? Okay, so you're going to put mu J equals UW. Assume that both the diets were the same. UJ. Now I have to look. Is diet is more effective in terms of weight loss? Okay, this is the weight loss. If you look, summary statistics for the weight loss. So a bigger number means more weight loss. So I want J to be bigger than W. Now, you have to define your parameters. Just by looking at your test, the ones that I looked at, nobody's defining the parameters. They had forgotten. So make sure you define your parameters. So this is the true mean weight loss for all large dogs that eat, not ate, that eat diet J. What's mu W? Okay, the same thing, but diet W. Okay, that's one. Okay, now let's go to section 2, which is this is the state, this is the plan, these are the conditions. Okay, I'm going to let you know now. I didn't check the report. I didn't check the grading guidelines, but I'm almost positive they're going to say you, as a student, have to say randomly assigned. They're probably going to make you say that, okay? Randomly assigned. You don't have to do the 10% condition. Okay, for means, it's not large count because we don't have counts. Count would be something that you're measuring a yes-no situation. We have large sample. And I know it's been a while, but we have to just remember this stuff, okay? All right, large sample. Now, you have two different groups. You have diet J, and we have diet W. Now, does diet J have more than 30? That's large count. No, there's not 30 or more. There's not 30 or more here. Okay, so the 30 or more is the central limit theorem. If the central limit theorem doesn't work, then we're okay if the population distribution is normally distributed, which they tell us is true right here. Diet J is normally distributed. It's given that both weight loss distributions are roughly normal. Let me write a little more neater if I can. Okay? Okay, so we have large sample. If you don't have 30 or more, then the population distribution has to be normally distributed. Now, if they wouldn't have said this stuff, and if they wouldn't have said this in the problem, then they would have had to give us 16 weight losses, and you would have had to graph those 16 weight losses and look for outliers of skewness. Okay. Now the third section is the do. Now once you're done with this, this is a two-sample t-test for just put for means. Okay. Once you write this, you could just run the test on your calculator, and you need a t and you need a p-value. Okay. So that's where you go to your calculator and stat, it's going to be two-sample t-test. I probably passed it. Two-sample t-test. Okay, so we want the average. You could fast forward a little bit if you want. Okay, got mean, standard deviation, data. Mean, standard deviation. But I want the first mu to be bigger than the second mu. Okay? That sign should always match your HA, which it does. That's it. It's a right tail test. See what we have. Okay, 3.29. Let me just make sure I don't have any mistakes. 3.7.52, 6.379, 0.819. Okay, everything looks legit. So even though the difference wasn't that big, this showed a significant difference, probably because these standard deviations were so small. 3.3. And the p-value was 0.002. And since this was a t, I'll just go ahead and write the df down just in case. 23. This p-value came from a t model that's the df of 23. They gave us an alpha. Okay, so now I'm on step 4, which is to conclude. Because 0.002 is less than 0.05, we reject H0. You don't talk about H0. You just reject it. You talk about HA. J is more. Okay. Our data found convincing evidence. You could write at a 5% level if you want. That diet J is more effective Okay, I'm not going to write this whole thing out, but let me just write that. More effective in terms of mean. If you don't say this word mean, they're going to ding you. I'm just letting you know. Weight loss. Blah, 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 blah. Right all the way to used in study. Okay? So 4 steps. No alternative, define the parameters. Step 2, conditions. Step 3, get the test statistic and the p-value. Step 4, make your decision based off the p-value. And then, talk about your HA terms of evidence. Okay, last one. Okay, so you're getting this table, and they're looking for an association. So this is going to be a chi-square test for independence. Okay, so here's your null. Don't just say no association here, okay? You need context. So there's no association between age group and say gender. In the diagnosis of, you could write in the diagnosis if you want. Okay, yes, association between age group and gender. Okay, perfect. Step 1. There's your no. Step 2, conditions. Alright, so on this one, let's see how they got these people. They got a random sample. It's not an experiment. Okay, all expecteds or greater than or equal to 5. So we're going to have to check that. Now to get the expected, just to let you know, just to get the expected, if you wanted to get the expected for women in 20 to 29, what you would do is you do 119 times 99 divided by 207. So what if you wanted women in 30 to 39? What you would do is you do 119, that's the row total for the women, and you would do times 63, that's the column total, divided by 207. So you could personally do them all out because there's only 6 of them if you wanted to. Okay, but we're not going to do that. We'll do it in the matrix. Okay, 3, and I named my test, so I'm good. I named it up here. So I don't have to show a formula. All I have to do is run it. Go back to my trusty calendar. Okay, now chi-squared is going to be a matrix. So I'm going to second x negative 1. Go to edit, and we have a 2 by 3, I believe. Make sure I'm right. Okay, 46. You want to zoom ahead a little bit, you can. I know it's getting kind of long. I just realized we have another row that I missed. Forgot the 50, 59s. So it's a 2 by 4. 23. And these are all counts. These are all observed counts. These are all observed counts. Okay, boom, we got those in. I'm just going to double check to make sure I got them. 53, 23, 93. Okay, good. Once you get those in, you can just go run the test. So hit stat, go over to test. Look, I hit the up button this time, chi-square test. Boom. And we are good to go. So 10.88 and 0.0123. Feels like something's wrong on one of them. 10.88. Point 0.0124. All right. So let me just put the DF just for fun, because it's always be good. So 1, 2, 3, 4. 4 minus 1. 1, 2. 2 minus 1. That's 1 times 3. So your DF is 3. It probably told you that when you ran the test. I think it tells you on. Yeah, there you go. Okay, there it tells you. Okay, what are we going to do here? We are going to, 0.0124 is less than 5% alpha. Since this is true, we reject H0. We found convincing statistical evidence of, and I'm just recopying it. I'm literally just writing it over again. You start making it up on your own. You can make mistakes. Sometimes they won't give it to you in a way to write back, but I'd say 90% of the time they do. Okay, so that's the second one. If you made it this long, for some reason I'm thinking that this p-value is wrong. So what I'm going to do is I'm just going to just look at my data, my 2 sample t-test, because I just remember looking at it and 2 sample t-interval. Just going to do it really fast. If it's right and you've already seen it, then you could just move on. And then 0.819. Oh, that's wrong. 16 dogs in there. How about 6.3? I thought I double checked. What am I doing on the interval? Darn it. Didn't even have my surgery yet. Okay, hopefully I kept it. 2 sample T test. Okay, I was wondering why that wasn't there. 2.523, 0.819, that's right. 6.379, 1.012, 16. I don't know. Seems right. So maybe I am right. Oh, here we go. This is right. I knew something was wrong. I knew it. Okay. You think hope for this. 7.4 e to the negative 4. Okay, so this is 7.4 times 10 to the negative 4. That's very small. Which, the way you do it is you just move the decimal that many places. So 7.4, 1, 2, 3, 4. Drop your dot. So that's 1, 2, that's 3 zeros. 1, 2, 3, 7. Must have hit something wrong. 7. Oh, I did that. 3.5. And this is 3.5. All right, so that's the review. And go ahead and learn from your mistakes. Most of all, with these multiple choice, because once you get these multiple choice, there's not a lot of different ways they could ask you. Okay, you run a test, you make a decision off a test. They give you a p-value, you make a decision off that p-value. A lot of the questions on this test was geared towards that. So, all right, I hope to see you next Thursday.